Hello everyone, I'm Timothy Samuel, doing my economics honors at Shivaji College. So I'm going to explain to you James Tobin's portfolio parents approach to demand for money. So there are a number of economists who have proposed their own theories to explain how people demand money. That includes Keynes himself and Tobin, of course. So what Tobin does is he actually extends or adds to what Keynes already explained. So Keynes completely ignored risk when it came to investing in bonds. Tobin adds that to his theory. And therefore, it is a natural extension to what Keynes proposed. So let's get into it. So as I said, it begins with the same equation that Keynes used as well. So he starts with E, which is E stands for earnings, total earnings, and that equals the market rate of return plus the capital gain. So capital gain is final, that is the final price at which you sell the bond, subtracted. That is that price minus the price at which you bought. That is the capital gain. So that and the market rate of return gives you the total earnings. And this capital gain holds this formula because it is a simplification of the explanation, which is the fixed income on the bond upon the expected return, because you're going to sell it somewhere in the future, minus the fixed income on the bond upon the rate of return of the bond at the time you purchased it, upon the initial price upon the bond, upon the rate of return. So this, when simplified, you end up with this, and that is what is written there. So Tobin includes this RE, which is expected return, which Keynes did not. So because he is introducing risk considerations into the determination of the demand for money. So he says that rather than some fixed expected capital gain, he assumes that the asset holder will have in his mind a bunch of capital gains, which he expects, along with probabilities attached to each. So that makes a normal distribution of expected capital gains. So a symmetric bell-shaped distribution, normal distribution, has given this figure, with the probability attached to the probability the capital gain on the y-axis. So that is this is the probability of this capital gain, and sigma g to the left and to the right, that is on either side of this capital gain, that measures the risk or the uncertainty connected to this capital gain, which constructs this normal distribution. So this sigma, which is the standard deviation, tells you how uncertain this capital gain is. So it is on either side. So G bar minus sigma G to G bar plus sigma G. If I can try to write that quite big. Okay. So G bar plus sigma G on the right, that the area between G bar minus sigma G on the left and G bar plus sigma G on the right, that holds the complete probability of whether this, of how much this capital gain is probably going to occur or not. So in this example, if you take this figure, it looks as if um, it looks as if two-thirds area is covered with the standard deviation and the capital gain. So in other words, you could say that 66.7%, that is using Chebyshev's theorem and other theorems, you could say that probably around 66.7% chance uh, chance exists that this capital gain along with this deviation can occur. So that is what we interpret from this. That is the statistical significance. Um, that gives you the probability through this normal distribution of this capital gain. So if you, for example, if you take G bar, the expected capital gain to be 10%, and sigma G, that is the standard deviation that measures the uncertainty of the capital gain to be 2%, we can say that there is a two-thirds chance that actual G will be between 8 and 12%. So through this figure, we see that this F1, this distribution is narrower. So the capital gains here is quite certain because sigma G is very small. So uncertainty is very small. Therefore, in other words, there is more certainty regarding this capital gain being received. On the other hand, F2, this much wider distribution, shows that sigma G is quite bigger, relatively bigger. So uncertainty is more. So you can identify more risk with this capital gain. So because you have introduced risk here into this approach, expected capital gain becomes E bar. So E bar equals R plus G bar. Now, if an investor, an asset holder puts B amount of his liquid assets, B rupees of his liquid assets into bonds, his total return will be B times E, just this. And the total standard deviation will be P times sigma G. Now, if you kind of um, add something to this, you get this. Just B equals, that is, you're taking sigma G to the left-hand side, sigma T upon sigma G. And you use this equation to substitute B in equation 12. You end up with this. And you differentiate this. You get R plus G bar upon sigma G. Now, to understand what this actually means, there is the differentiation of total return RT. Let's take some numbers. So if we say R is 5%, G bar is 10%, sigma G is 5%, then this differentiation, this equation will be 3. So to interpret this, we understand this as an increase of 1 percentage point in the standard deviation in the total portfolio, which is sigma T. Increase of 1 percentage point in this will yield you a 3% increase in expected total return RT with the given values. So that is how we interpret this. So this budget constraint in equation 15 and 14, we can find it, that is, we can plot it in a graph. So here we find this. This is the x-axis, which is measured by sigma T, total standard deviation, and total return is the y-axis. So this budget constraint which is the differentiation. That is, in other words, the slope, first order differentiation. The differentiation here, differentiation of RT, that is R plus G bar upon sigma G. So you find that here, that makes this budget constraint. And here, below this x-axis, so out of the total wealth of an asset holder, he can either invest it into bonds or he can have it for using, that is money. So the area from 0 downwards is B, and the area from downwards towards 0 captures M, which is money. B stands for bonds out of his total wealth. And this budget constraint is 1 upon sigma G. That is, if you differentiate B, you end up with this, right? For example, I'll try to do it. Now differentiating B in equation 14. Differentiating B, now you again get the slope, similar to equation 16. Get 1 by alpha, 1 by sigma G. It's quite tough here. Okay, so this this gives you the, sorry. So this gives you this, this slope, this first order differentiation of the bond, that is how much liquid money you put into this, gives you this slope below the below the x-axis, below it. So this is how you kind of plot the budget constraint for. This is an individual's portfolio analysis, an individual's portfolio decision. So this is how it appears. Individual trading, increased risk or increased return. So we can also find here that to find the amount of liquid money he puts into bonds, to find that for any given value of sigma t, it's total risk. When the risk is given, to find the bonds he is going to put, you can multiply 1 by sigma g with that sigma t to find B, because we found that here. That is the equation. So to get B, we multiply both these expressions, or we can also try to reflect it from the line with the slope 1 by sigma g in this bottom half. So this length of the vertical axis below the y-axis is total liquid wealth. Distance from the origin along this axis gives total bond holdings, and the remaining distance gives you money holdings, M. Now to locate B, we have this hack. To find the equilibrium risk and return, that is sigma t and RT on this top half of the figure, we need to understand the individual's risk and return preferences. So we have different cases for that. To know how the individual, the asset holder, chooses to invest. So there are in major there are two preferences. One is risk averters and the other is risk lovers. So risk averters are those who are risk averse. They don't want to take more risk. So their indifference curves, as seen here in these three figures, their indifference curves have positive slope, which we interpret as they want more return to uh, take more risk. So that is how they trade off. So only when more return is uh, displayed before them will they be fine with taking more risk. That is how we look at this graph. So the first case here is specifically called a diversifier. So this specific name is because he puts money into both bonds and holds money. And since it is upward sloping, it is convex to the budget line, and you see it it is tangent at this point. So total um, the total uncertainty or the total risk is measured here. While reflected, you find how much money he holds and how much he puts into bonds. So this is a diversifier, and since the indifference curve is upward sloping, it is a typical case of an indifference curve. So the highest indifference curve, which is tangent to the budget line, is picked. So that is what he tries to do. Um, as the risk increases, he increases his demand for more return. So this is a more practical case. The other two cases are called plungers, who either put their money completely into bonds or don't even put. The first one is um, the indifference curves are quite more steep than the budget line. And you find here that it is touching the budget line at this vertex here at 0 at the meeting point of y-axis and x-axis. So you see, he does not hold money at all. Sorry, he does not hold bonds at all. Bonds is completely 0. He holds uh, money 100%, completely money. The opposite to this is this figure where he does not hold money at all, completely bonds. Because you find U1, the utility or the indifference curve, touching the budget line at this corner. So while trying to imagine its reflection, you find 0 money and completely money held in bonds. So these three cases are examples of risk averters. Now you find this figure as an example for risk lovers. So here the indifference curve is not upward sloping or does not have a positive slope. It is downward sloping, negative slope, which means he doesn't bother. He is a risk lover. So he is not looking for more risk. Sorry, he is not looking for more return to assume more risk. He is okay with it. And since he's a risk lover, he also holds his money completely in bonds. Therefore, you find the indifference curve touching the budget line here, which means 0 money and completely bonds. So he's a risk lover. This is his utility curve. He also attempts to maximize risk. So he puts his entire wealth into bonds, like this plunger. So out of all these four cases, the diversifier uh, is a quite general, practical version of an asset holder in reality. So that is how uh, asset holders behave, and that is how people demand money, according to James Tobin. Uh, so this is the portfolio balance approach and the theory proposed by James Tobin, and he thinks that is this is how people demand money. So I hope you had a good time understanding uh, Tobin's approach for the demand for money. Thank you.